Good afternoon, everyone. Let us start. Today we shall learn a new chapter, Chapter 9, Solar Radiation, Heat Balance and Temperature of your NCERT textbook, Fundamentals of Physical Geography. Now I will present my screen. So this is the chapter, Solar Radiation, Heat Balance and Temperature, Chapter 9. Now let us read. We know that Earth receives almost all of its energy from the Sun. And the Earth in turn radiates back to space the energy received from the Sun. As a result, the Earth neither warms up nor does it get cool over a period of time. Thus, the amount of heat received by different parts of the Earth is not the same. This variation causes pressure differences in the atmosphere, because we know that temperature and this pressure is related. And this leads to the transfer of heat from one region to the other by winds. So the ultimate source of energy for the Earth is the Sun. And if there were no Sun, then no weather phenomena, no life on the Earth, no water on the Earth. It is only because of the Sun that we have all the activities. Now we have solar radiation. What do you mean by solar radiation? Let us read. Earth's surface receives most of its energy in short wavelength. Earth's surface receives most of its energy in short wavelengths. That is in the form of electromagnetic waves. Do you remember what wavelength is? See. This is the wave. So this is the wave, and the Sun emits energy in the form of waves. Different waves, mainly in the form of short wave. And here the highest point is known as crash, and this is also known as crash, and this is known as trough. So distance between the two crests. So here we have a crest and another crest is here, and distance between these two crests is known as wavelength. This is what we call wavelength, and it is denoted by lambda. So the Sun radiates energy mainly in the form of short waves, and the energy received by the Earth is known as incoming solar radiation, which is in short term as insolation. The energy, the amount of energy received by the Earth from the Sun is known as insolation, a short form of this incoming solar radiation. So here we have in, then solar, then we have Sun, insolation. Short form of incoming solar radiation. You must know that we get a little amount of energy from the Sun. It is said that only 1/2000 of a billion of energy is received by the Earth from the Sun. And the arc, okay, we know that the arc is geoid resembling a sphere, and the sun's rays fall obliquely at the top of the atmosphere, and the arc intercepts a very small portion of the sun's energy. We know that the shape of the arc is geoid. Okay, it is flattened at the poles. Okay, the shape of the arc is geoid in this way, flattened at the poles. And here we have the atmosphere. Okay, the atmosphere is also covering like this. Okay, and here the energy received here, okay, received at the top of the this atmosphere is oblique. Okay, in most of the places it is oblique, that is inclined. Okay, in most of the places it is inclined here. Okay, actually we must draw like this. See. Okay, see here, and it is vertical at this equator, and if you draw a tangent here, you will find that it is inclined. Okay, it is less than 90 degree. That means the sun's rays, okay, which fall on the top of the atmosphere is inclined. It is inclined, it is oblique. Okay, it is inclined like this. Okay, and that is why, okay, arc receives a very small portion of the sun's energy, and on an average the arc receives 1.94 calories per square centimeter per minute at the top of the atmosphere. So at the top of the atmosphere, the Earth receives only 1.94 calorie per square centimeter per minute, and this is termed as solar constant. Okay, this value is known as solar constant, and with this amount, okay, the whole weather phenomena life on the Earth exists. The solar output received at the top of the atmosphere varies slightly in a year due to variations in the distance between the Earth and the Sun. Okay, so we know that this orbit, okay, orbit means the path of the this Earth around the Sun is not a complete circle. It is elliptical. Okay, it is elliptical, and that is why the solar energy received at the top of the atmosphere varies slightly in a year due to variation in the distance between the Earth and the Sun. So during its revolution around the Sun, okay, the Earth is the farthest from the Sun. That is around 152 million kilometers on 4th July. And this position of the Earth is called aphelion. And again on 3rd January, the Earth is the nearest to the Sun, about 147 million kilometer. And this position of the Earth is called perihelion. Okay, see here, just see here, see this diagram, and see here on 3rd or 4th July. Okay, the distance between the this Earth and Sun is the farthest. So it is about 152 million kilometers, okay, from the Sun, and this position of the Earth is known as aphelion. It is either on 3rd July or 4th July. And again in January, on 3rd January, okay, the distance between the Earth and the Sun is the shortest, nearest. Okay, it is 147 million kilometers, and this position of the Earth, say of the earth is known as perihelion. Okay, remember perihelion means nearest to the sun, and aphelion means farthest, okay, from the sun. And accordingly, see, you'll find a little difference, okay. That is why see the annual insolation, okay, therefore the annual insolation, that is the amount of energy received by the earth on 3rd January is slightly more than the amount received on 4th July on the top of the atmosphere. Okay, on the top of the atmosphere, see, the amount of energy received by the earth is slightly more on 3rd January than on this 4th July. This is because of the differences in between the distance, okay, differences between the earth and the sun. And but you must know that January, you know, say we are in the northern hemisphere, and in January we have this winter season. But you must know that this winter season and the summer season is not caused by the distance between the sun and the earth. It is merely caused by the inclination of the earth axis towards the sun. Okay, and that is why, see, the effect of this variation in the solar output is marked by the other factors like distribution of land and sea and the atmospheric circulation. Okay. So any question from your side regarding insolation? Insolation means amount of this energy received by the earth from the sun. Okay, if you don't have, then let us proceed. Okay. So variability of insolation at the surface of the earth. We have learned that there is variation, there is differences in the amount of insolation, okay, received on the surface of the earth from place to place. And this amount also may vary say during a day and during say between the seasons and in a year also. Say in a daytime, okay, in a day also, when we compare this early morning and noontime, then we feel, okay, we feel hot in the noontime. That means we find variation in the insolation, amount of insolation, okay, between morning and noontime. So we have many factors, okay. The factors that cause this variation in insolation are, say, number one, we have this rotation of the earth on its axis. Okay, number one factor is rotation of the earth on its axis. This is very simple. We know that the earth is rotating on its own axis. Okay, earth is rotating on its own axis. Everybody knows that. Suppose this is the earth, and see, earth is rotating. See, this is the axis. Okay, and this earth is rotating on its own axis from west to the east. Okay, and see, because of this we have this daytime, nighttime, you have learned earlier. Okay, see here, let us suppose see, the sun's rays is striking on this side of the earth, and hence this side is the daytime, and the other side, okay, this side is the nighttime. So in this way, because of the geoid shape of the earth and the rotation of the earth on its own axis, we find variation in the amount of insolation in a day. Okay, so we get sunlight, okay, half of the earth, and the other half we don't find sunlight. So in this way, because of rotation, there is variation in the amount of insolation. Then number two, we have angle of this inclination of the sun's rays. Okay, angle of inclination of the sun's rays. For this, let us see this diagram. See here we have the equator, and this is the atmosphere, and we have the earth here. Okay, sorry, this is the earth, and see here, see at the equator. Okay, at the equator we find these vertical rays. Okay, vertical rays of the sun. And away from the equator, here we find these inclined rays of the sun. Okay, inclined. See here, if we draw a tangent, then the angle formed here is less than 90 degree, and here, okay, it is almost vertical. Okay, actually I am telling about the thermal equator. So this is the real one, and this is the thermal equator. Okay, and see, we know that the inclined rays, okay, the inclined rays covers a larger area. See, the inclined rays cover a larger area as compared to the vertical rays, and hence in this case, in case of inclined rays, the heat is distributed over a greater area, and that is why we feel cold. And on the other hand, here in case of vertical rays, the heat is concentrated in a small area, and that is why it is heated quickly and we feel hot. Okay, so in this way, due to the inclination of the sun's rays on the earth, okay, on the surface, there is a variation in the amount of insolation. You also may find that in summer, in the early morning, the sun's ray, okay, are inclined, and that is why we feel this cold. Likewise, in the this evening also, we feel somewhat colder than the noontime, because we get inclined rays of the sun. Whereas in the noontime, say we get almost vertical rays of the sun, and that is why we feel hot. And it is explained in this way. Okay, vertical rays covers a small area, whereas inclined rays cover a larger area, and the heat is distributed over a greater area, and that is why we feel cold. Okay, next we have length of the day. Okay, length of the day. This is mainly due to the inclination of the this earth axis towards the sun. Okay, here let us see this diagram. See, in this case, so in this case, here this is the equator. Okay, this is equator, this is Tropic of Capricorn, this is Tropic of Cancer, and this is Arctic Circle, and this is Antarctic Circle. Okay, so on December 21 or 22, we will get vertical rays this along the this Tropic of Cancer, sorry, Tropic of Capricorn. Okay, on December 21 or 22, say we will get vertical rays of the sun along the Tropic of Capricorn, that is 23.5 degrees south. Okay, 23.5 degrees south latitude. And on this day, say you will get this longest, you will get longest daytime and the shortest night time. And so during this period, the southern hemisphere, okay, the southern hemisphere will have this summer season. Okay, so on the other hand, see, we are in the northern hemisphere, and that is why on this day, on December 21 or 22, we will get the longest night time and the shortest daytime. Okay, when the daytime is short, then we will get less insolation. And remember, say in December, say we are in the this winter season, because here during this time we get these inclined rays of the sun. Here in the northern hemisphere we get inclined rays of the sun. That means the sun is going to the south. Okay, and here in the southern hemisphere, say they get these almost vertical rays of the sun. So in the other case, say on June 21 and or 22, okay, on June 21 or 22, see along the this tropic of Cancer. So this is the tropic of Cancer, this is the equator, and this is the tropic of Capricorn. Okay, so on this day, say we will get vertical rays of the sun, this along the this tropic of Cancer, that is 23.5 degree north. So on this day, we shall experience this longest daytime and the shortest night time. On the other hand, this in the southern hemisphere, okay, in the southern hemisphere along the this tropic of Capricorn, they will experience the reverse. Okay, so they will experience the this longest night time. And you must know that during this time, see the northern hemisphere will experience the summer season, because see here the earth axis is inclined. Okay, the earth axis is inclined towards the sun, and that is why the northern hemisphere gets these vertical rays of the sun, and that is why the northern hemisphere is in summer season. And in this position, okay, see the here is the axis, and the earth axis is inclined away from the sun, and that is why this northern hemisphere is in this winter season. Okay, and we have two more position. Okay, in this case the earth axis is not inclining towards the sun. Okay, in this case also, and in this case also, axis, the earth axis is not inclining towards the sun. Okay, neutral. So during this time, see in the this on March 21 or 22, so here in this case we will get equal daytime and equal night time. Okay, say along the equator and tropic of Cancer, Capricorn, we will get equal night time, and that is why this is known as equinox. Equinox means equal night. Okay, nocturnal means night time. And so in this position also, it is on September 22 or 23. So in this case also we shall get this equal night, equal this night time and equal daytime, that is 12 hours daytime and 12 hours this night time. And these two position is known as solstices. Okay, and this is the case of winter solstice, and this is the case of summer solstice. And this equinox is known as spring equinox or vernal equinox, and this is known as autumnal equinox. Okay, so in this way the length of the day, okay, is mainly caused by the this rotation of the earth on its own axis, then its inclination towards the sun or away from the sun, and its movement in an elliptical this path. Okay, and accordingly this insolation is also different. And the fourth one, we have transparency of the atmosphere. See, when the atmosphere is very clean, okay, when the atmosphere is very clean, then we will get bright sunshine. And when we have a lot of dust particle and a smoke particle, then we get a less amount of insolation. Say, for example, in the month of February, okay, when we have burning in the forest for shifting cultivation, due to the smoke in the sky, we get less sunlight, okay, less insolation, and that is what we call transparency. Okay, so in the month of February we have less transparency, we have lot of dust particle and smoke particles in the atmosphere, and accordingly the amount of insolation is different. And the last one, number 5, the configuration of lane in terms of its aspect. Okay, so this is, it means aspect means the direction of the slope. Okay, this one I have explained you many times. And about these mountain range, I have explained you many times. Okay, so in this case, let us suppose this mountain range is running east-west direction. Okay, east-west direction, and in the northern hemisphere, it is located in the northern hemisphere. And when a mountain range runs east-west direction in the northern hemisphere, then generally we get more sunshine on the southern slope than the northern slope. Okay, so in this way, the direction of slope, that is aspect, also determines the amount of insolation. And I also have explained you about the house also. If your house is facing towards the east in the northern hemisphere, then your southern side of your house will get more sunshine than the northern side, mainly in this winter season. So in this way, the direction of slope also determines the amount of insolation. So any question from your side? Okay, if you don't have, then let me proceed. About the angle inclination, we have explained you earlier. Okay, and about this also we have explained using a different diagram. Okay, then and here about this we have learned earlier, the atmosphere is largely transparent to short-wave solar radiation. This is about greenhouse effect that was discussed in the previous chapter. Okay, incoming solar radiation passes through the atmosphere before striking the earth, and that sunlight is again absorbed by the earth, radiated back into the atmosphere in the form of infrared, that is long-wave terrestrial radiation. And this infrared radiation will be absorbed by this water vapor in the troposphere, then carbon dioxide and dust particles, and the earth is heated. That is what we call greenhouse effect. Then we also have learned that very small suspended particles in the troposphere scatter visible spectrum both to the space and towards the earth's surface. And this process adds a color to the sky. The red color of the rising and setting sun and the blue color of the sky are the result of scattering of light within the atmosphere. Do you remember the 7 colors of this sunlight?
Yes, sir.
Tell me. See here. Okay, Bib Gior, do you remember? See, we have violet, then next we have indigo, then blue, green, yellow, orange, and red. Okay, so this side of the spectrum okay, has the shortest wavelength, and this is the longest. Okay, in this case, in the visible spectrum, orange and red have the longest wavelength, and violet, indigo, blue, these have the shortest one. Okay, so these colors, visible colors, are scattered in the sky. And see here, see this diagram. Okay, see here we have so many particles in the atmosphere. We have gas molecules in the atmosphere, and these gas molecules and the dust particles scatter the visible light in different direction. Okay, so this is the diagram showing scattering. And see here, the particle or the gas molecule is scattering the light in different directions. See in this case also. And generally we have 2 types of scattering. One is known as the Rayleigh scattering, another one is the Mie scattering. And the blue color of the sky is merely caused by the Rayleigh scattering. Okay, so in this case, the shorter wavelengths like these violet, indigo, and blue are scattered. okay, in the sky by the very small these gas molecules and these dust particles, and that is why we see blue color of the sky. So okay, so in this case, in the case of Rayleigh, the diameter of the particle is very small, okay, or the diameter of the gas molecule is very small. So diameter of the these molecules, gas molecules or dust particle, is smaller, okay, is smaller than the wavelength. Suppose this is the wavelength and the size of the particle is smaller than the wavelength. And in the case of this Mie scattering, okay, here the diameter of the these gas molecules or these particles, dust particles in the atmosphere, is greater than the this wavelength, and hence so you will get this Mie scattering. And because of the Mie scattering, so you will see white layer around the sun, okay. But about the this red color, I think you may be seeing red color or orange color sky in the early morning or in the this night time. That is because when, let us say, this is the earth, okay, and here we have the atmosphere, and when the sun is setting, okay, so here it passes a longer path in this way, okay, in this, so this is the noon time, and when in the early morning or in the evening, the sun is passing through a greater distance in the atmosphere, okay. And so during its travel in the atmosphere, most of the blue and these violet wavelengths are scattered out, okay, by the gas molecules and these dust particles, and consequently this the light that reaches our eyes consists mostly of red and oranges, and the reddish appearance of cloud during the sunrise or sunset, okay, are the result, okay, because these clouds are illuminated by the these orange and these red colors, and that is why we see this red or orange color in the sky in the early morning and in the this evening, okay. So all these blue color of the sky or this red or orange color of the sky in the morning or evening is due to scattering process, okay. And see about the spatial distribution of insolation, that is differences in the amount of insolation at the earth's surface. See, insolation received at the surface varies from about 320 watt per square meter in the tropics to about 70 watt per square meter at the poles, okay. At the polar area we get only 70 watt per square meter, whereas in the tropical region, okay, we get 320 watt per square meter. In this way the amount of insolation is varied, and a maximum this insolation is received over the tropical deserts, okay, over Sahara desert, then this other Atacama desert, then Kalahari desert, okay. In the desert areas we find maximum insolation because the cloudiness is the least. In the desert we find less clouds, we get bright sunshine. Equator receives comparatively less insolation than the tropics because this along the equator we have lot of clouds and a lot of this heavy rainfall along the equator, and that is why we get less insolation as compared to the tropical region. And sometimes say these places at the same latitude, okay, also get these differences in the insolation. see, we find more insolation over the continents, okay, than over the oceans also. So any question from your side?
No, sir.
Okay, then let us stop here for today. Thank you very much for joining my class.